Let's consider a data structure with a particular set of requirements. It has to be able to be traversed in sorted order reasonably quickly. It has to be able to insert and remove elements reasonably quickly. And it has to be fast to search for a particular element. The most intuitive solution one might immediately come up with is to have a linked list which is sorted upon insertion. What I mean by this is that when you modify the add step of this linked list, instead of inserting to the start or the end of the list, you traverse to the right place in the list and you insert there. For example, we have a linked list of integers which goes 1, 2, 4, 5, 6. We need to insert the number 3. We go 1 is too small, 2 is too small, 4 is too big, that's where 3 goes, before the 4 and after the 2. Makes sense? It's sorted at all times, we always have it sorted. To search, we just traverse through until we find the right number, because it's sorted. We know that if it's if it's going to be larger than the first number, it's going to be further along the list. If the number is larger in the list and it's not there, it could work, but it doesn't seem that fast once it gets really big. Let's take one that's 1,000 length. We have to search quite far through that 1,000 length list to get anywhere. And that might not be optimal. Maybe there's something more efficient we could do. And this is when we have to consider the use of our references, our pointers in these nodes, and what we could do with them. Do we just have to have one, or can we have multiple? And can we make some rules about where these pointers point to, which will help us in this endeavor? Well, what if we made our rules such that they helped us traverse this list in the most optimal possible way? And what if we just had a more helpful number of these references? Let's say that our nodes can point to 2 items. And let's make the rule that one of the items is less and one of the items is greater. You'll see very quickly how this can be useful. Let's start off with just one node at the top here. This node will have a value of 5. And let's say that the left node is less and the right node is bigger. So since the left node is less, we want to insert 3. We start with 5. 3 is less than 5, it goes to the left. Make sense? Simple. If the right is larger and we want to insert something to the right, let's say we're inserting 7, and now we have 7 to the right. So it goes 5 and then 7 if you try to find the largest element. To find the largest, you just go right, 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 right. Find the smallest, you just go left, 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 left. It's quite simple to find the largest and the smallest. But you might be wondering, what if I have a number that's larger than 5, but smaller than 7? It has to go to the right of 5, but then what does it do? Well, just keep in mind that this is a recursive sort of data structure. Every node has these 2 references. So we go 5, well, 6 is larger than 5, goes to the right. 6 is smaller than 7, so it has to go to the left of 7. So it goes 5, 7, and then to the left of 7 is 6. But now you might be wondering how we can make a useful traversal out of this. How do we get this into sorted order? Well, the sorted order question actually becomes a lot simpler if we consider how our recursion is done. We can traverse the list. It's not actually a list, it's nonlinear anymore. We can't really call it a list. We can traverse our nonlinear data structure, our tree, in such a way that we get into sort order by going left, center, right, or right, center, left. The way we can do this is we can follow through. Let's say we want to go largest to smallest, because that's where our tree right now is a little bit more complicated. It's a bit of a better example. We go to the rightmost, rightmost, rightmost node to get the largest for the start. And then what is the second largest? Well, the second largest is going to be what was the center of the subtree that the largest is in. What does that mean? Well, remember, this data structure is recursive, so every node can be considered the root of its own subtree. Let's visualize the subtree of just the system with the largest node. That subtree has its center node, its lesser node, and its greater node. But what do we know about this subtree? We know that every one of the nodes in this subtree is greater than the nodes above it, because it was on the right of the node above it. So we know that it must have been larger. Since we know that it must have been larger, we can say that it is indeed all larger. We just have to traverse this subtree in order. And to traverse this subtree in order, we go furthest to the right, then we go to the center, then we go to the left. And remember, when I say in order, I mean largest to smallest. So right, center, left is the in-order version of that subtree. And then we go through every other one of the subtrees, and we go right, center, left, right, center, left, right, center, left, until we get through the whole tree and we get it in the correct order. We go left, center, right if we want the opposite order of that. So if we want smallest to largest, we just go all the way to the left to get the smallest, then center, then right, left, center, right, left, center, right, left, center, right, and we get the smallest to the largest. How do we search? Well, at every step, we simply ask ourselves the question: is the one we're searching for less than or greater than the current node? So if we want to have another binary tree, let's say this one has a root of 0. And then, well, we know that negatives are going to be on one side and positives on the other. That way we can say, is our number negative or positive for the start? And let's say on one side we got -5, on the other side we got +5. Right? That's what our tree looks like right now. And I'm deliberately only telling us about the nodes we can see. We can only see the root, the left, and the right. That's all we need to see. Because we don't care about what's on the rest of the tree. That could be really large, really small. We don't care. We just care about what we're searching for. And let's say the number we're searching for is -3. So we go 0. Is it -3 positive or is it a negative? Well, it's a negative. So we can go, okay, it's towards the side of -5. But it's larger than -5. So it's got to be to the right of -5. So we go center, then we go left, then we go right. And what's the right of -5? Well, in this case, it was indeed -3. And then this sorting algorithm, the searching algorithm, I mean, can be applied across the board. To search through the tree, all we need to do is just ask ourselves, is it less than or greater than at every step? And if it's equal, that is a separate case, but it's not much different. We just have to set a condition that one of them also takes in the equal. So one of the sides is less than or equal to, one of the sides is greater than or equal to. So hopefully this made binary trees a little bit more clear and understandable for you guys. Good luck. Hopefully it helps with your coding. The tutorials do cover the coding implementation of a binary tree, and hopefully that'll be useful to you. Thank you so much for watching. Enjoy your day. Hello. Okay, hopefully y'all can hear me, and hopefully I didn't cut off the intro video too early. Alright, so maybe that intro video made binary trees a little bit more clear, but I'll go over it again just in case for the concept, and then we'll see about writing the code. So here I've got this old program that I made a while back, which demonstrates a binary tree visually. Now the point of a binary tree, again, is that it's a data structure which is not sorted upon insertion, but it can be used that way if you're willing to think about it like that. It sorts things sort of by their rank, and it inserts them left or right depending on what their rank or their sort position would be. Well, we'll see more detail as it comes up. First, let's try some insertions here. We've got 58 as our starting score. And now if we add something random, let's see which side it's going to go on. Here I'm going to click add random. And it's going to be 218, and it seems to have gone to the right. So here right appears to be larger, right? And let's prove that. Let's put something smaller as well. I'll make this one be, I believe it's month hired here. That's the important variables. 33, that's indeed on the left. So the smaller ones go to the left and the bigger ones go to the right. But what happens if something is both smaller than 58 and bigger than 33? Well, in that case, it's going to go recursively. It's going to go down here and it's going to apply the base case to 33. If it's smaller than 33, it goes to the left. If it's bigger, it goes to the right. Let's prove that. Let's add a custom cat. Let's see if we will give it a value of 50. Now 50, it goes right there. So hopefully that makes it kind of understandable how the insertions work. Let's just do some random ones here. Add random. Let's go again. It's 123. It goes 58, 218, 123. All right. Now add random again. 164. Yeah. Now I'm just gonna a few more times, and then we're building up a long tree, and we're seeing that here on the side, we've still got an in-order traversal, and it looks to be doing it well. We think it's quick, but it could be doing it slowly. It could just be a fast computer. You don't know, but it's doing it in reasonably fast time. So yeah. That's the sort of idea of a binary tree. We're supposed to add following this rule. We're supposed to add following the rule of, let's just remove everything. We're supposed to add following the rule of if it is smaller to the left, if it's larger to the right. Smaller left, larger right. That's our rule. Why is this rule helpful? Well, if we add a cat, let's say we're trying to find 176. But we're blind to what the heck is going on here. I'm just going to make us blind to it really quickly, like we saw in the intro video. If we're blind to what this stuff is, we see 201, 172, we're blind to what's bigger or smaller, but we know that 176, which side is it going to be on, left or right? It's going to be on the left because it's smaller. It's going to be on the left or right? It's going to be on the right because it's bigger, and lo and behold, that's exactly where it is. So that's the use of a binary tree. Now let's go about implementing it. But wait. Before we implement our binary tree, let's take a look at something here. in the project on GitHub, which we have a link to. I'm just going to send a link to the chat once again. If anybody needs to clone it, I'm going to explain things while I wait for you guys to clone, and hopefully by the time I'm finished explaining, everybody's cloned it. So here we've got a binary tree, and it's a generic tree, right? Just like last time. We made the generic linked list before. We've seen the E here. We made the generic sorting algorithm, but what we haven't seen is modifiers on our generic thing. Here, our E isn't just any E. It's not just any object. It's E extends comparable, which means we can put any object into our binary tree as long as it's comparable. Now, why do we care about comparable? We care about comparable because we need some way to score the items that go in our tree. We need some way to determine what goes to the left, what goes to the right. That's what comparable is for. It's an interface, which you'll be seeing in assignment 3 as well. And it's used to sort of to compare items, give a numerical value to the difference between two items. And here, our tester is going to be using pocket monsters. I'm sure we're all familiar with pocket monsters. We make them battle each other against their wills. This is our pocket monster class. Now, the problem here is that our binary tree test class doesn't see the pocket monster compare to, and we can't create a binary tree with a pocket monster because here it says type parameter pocket monster is not within its bound, should implement comparable, but it doesn't implement comparable. So why don't we go fix that right now, and let's deal with the lack of implementing comparable. I'd like to reiterate once again that comparable is an interface. An interface is like a class, it's like an abstract class, but it has no methods defined. It's like a template. You are there to define your methods. It doesn't define anything, it just tells you what you have to have. It's like the list of what you need to get done, but not how you're going to do it. And here in IntelliJ, we can see that it'll automatically allow us to implement the methods we need to implement. Here, it's just compare to. And here, we're just comparing a pocket monster to a pocket monster. Now, remember to access the values in the pocket monster we're comparing, we use this. So we could say, let's say, int my health equals this dot get health. Or actually, you know what? We don't want health. We want to compare. Let's say that we're scoring them based on. Let's think about it. They've got main properties here like damage, health. Yeah, okay. So why don't we compare how powerful they are by how much damage they can do, plus how powerful, like how much health they have. So yeah, and then maybe. Yeah, I think that should be a simple enough point of comparison. Let's keep it simple for now so we can test our stuff. We can make it more complicated later if we choose to. So int my score is equal to this dot damage plus this dot get HP. And it's okay to do either the field access or access, like directly accessing the field or accessing the field through the getters. Both will work. Here I'm going to call the getters just to be fancy about it. And then int their score is equal to o dot get damage plus o dot get HP. Now this is how we're going to make our comparison fair. We're doing the same thing with both. We don't have to make it fair if we don't want to, but it's better if it is, so our method makes sense. And now we can simply return our score minus their score. Let's see if that actually works well for us, because we have to consider the way that this is expected to use. The iterator must also ensure that the relation is transitive. Yeah, okay. Finally, x compared to y is 0 implies that they're equal. Okay. Must ensure that okay, sign compared to x is equal to negative sign implies that x compared to y must throw an exception. But here's the important part: return a negative integer, 0 a positive integer is as this object is less than, equal to, or greater than. So if this object is less, it's a negative integer. And that is good. So it is indeed my score minus their score. Now I'm checking this logic with a little bit of care because this is kind of important. This is what's going to be used to sort things. If we get it backwards, it's not a huge deal, but we'll have things reversed. And we'll be like my last tutorial on Monday where I spent way too long debugging the tree when in reality the only thing I did wrong was I was sloppy here and I did the wrong order for the minusing. That's a mistake that's really common. I mean, I made it, and I'm just making sure that this time it's avoided, and it's a good thing for everybody to do just to ensure that that doesn't happen. It's a really annoying thing to sort out. It's really easy to debug if you catch it, but it can cause you a lot of pain. Okay, so that's the compare to done. That's comparable. It's a really easy interface. Now we can get to the binary tree. Pocket monster compare to. Oh, it looks like it doesn't like that. Let's see, pocket monster compare to. That's how we're supposed to do it. That's the right notation. I've got a zoom sound. I don't know what that zoom sound actually means, but if somebody came or left or something, I don't know. The ding 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 has occurred. So if you have a question or something, you're welcome to talk and I will answer. If you don't have a question and that ding is for a reason that isn't because you have a question, ignore me. All right, so here we have a binary tree. And the first thing I want to do is to create the method which adds something to the binary tree. Now, we're adding something to the binary tree, which means that we're first setting our root if it's not there. This is like a linked list. I like to write mine without dummies. I think dummies are dumb. I avoid them. I say keep the root null if it's empty. If it's empty, then you just add the thing to be the root. So if root is null, root is equal to new tree node data. And we'll also say size plus plus. Right, now that should be relatively simple for you. We're setting the root to not be null when it is null. And we're setting it to have a value, and we're increasing its size such that, well, the size of the tree is tracked properly. If there's any questions, I'm happy to answer. Otherwise, I will continue on. I'll give you as a sec. Next, we're going to have to hit the recursion. So it's going to be a little bit, maybe harder to follow if you're not super comfortable with recursion, but that's okay. I'll make sure it's really simple for everyone. So when the recursive step of add, what we have to do is we have to create our recursive helper method. I like to keep these private. Some absolute mad lads like to do their methods publicly, like their recursive ones, and they like to expose their nodes to the public. I say the public cannot be trusted with our nodes, and we should do these methods privately. The data tree node e node. All right, so this is our recursive add method. And of course here I want to call the recursive method if the non-recursive method has indeed not run. So add data, and then here as the node I'm going to add to is going to be root. Now the add method is quite simple, but deceptively so. Here goes. So if data dot compare to node.getData is greater than 0. What are we going to do? Well, this is where we decide what left means and what right means. I'm going to say that this is going to be left. So in this condition where the data is greater than the data in the existing node, we're going to go left. Left is larger? Sure. Node.getLeft is null. Well, we just have to put the new node there. So what this means is if this data is larger, right, and we want to follow our binary trees rule and say, well, lefty larger is not the rule being followed here. Here it's righty larger, but whatever. You should hopefully get that, right? Like it's one of the sides is going to be larger. So here, let's say we want to add, well, I'll restart it again. I'll do a base case add just so it's real simple. 101, we're going to add something. Now, if that thing is going to be bigger, it's going to be on one side. If it's going to be larger, it'll necessarily be on the other. There, it was larger, so here it went on the right. So 101 went to the right, it became larger, it became 177. Right, and then that was just added because there was no node there before. If I add another one, let's see, is it going to go, yeah, it's going to be even larger, and then it gets added to the right of that, recursively. So if the node where it's supposed to go is null, it gets added there. If there is already a node there, it recursively gets added to the next spot, as we previously explained. So if it is null, we say node.setLeft new tree node data. And then size plus plus, because obviously we do want to increment the size if we increase the size of our tree. Now else, we just want to recurse down towards that node, right? We want, if that isn't null, that means there's another subtree there. So we can continue our recursion here. We can just say data node dot left, or get left, right? We want to use our getters just to be fancy. We don't have to use our getters if we don't want to, right? Now else, we just do the exact same thing but the opposite. By the exact same thing but the opposite, I mean is if we're not adding to the left, it's got to be the right. So we just got to get everything to be the right. And where it used to be left, it is now right. So this is going to be set right. This is going to be node.getRight. Everything that was once left is now right. and that is quite similar. You'll see a lot of these symmetries writing binary tree methods. Indeed, basically every method you write for a binary tree, you can expect to see this kind of symmetry, where you go do something on the left or the right, and then you do the one on the other side. So you do something on side A, maybe you do something in the middle, you do something on side B. That tends to be how these binary tree methods run. Now, if we want to make sure our add works, we can test out our add. Now, it's not going to work yet because we don't have an in-order method written. But what we could do is we could run it with the debugger, and we can just see if the add is doing its job properly. I'm just going to put a breakpoint in here, and we're going to watch the tree as it grows. So first thing we want to do is, oh, and the sunset out there is gorgeous right now. I'm so sorry if you guys are actually watching this live with me. To all of you who are watching it live, I am deeply sorry that you're missing that sunset right now, because God, it's gorgeous. Anyways, so we're gonna see it's of size 0 right now. The list is of size 0, but our tree shouldn't be because something should already have been added. And it's the root, both left and right is null, and it's a Pokemon named Website. That is an adorable name. So Website here has an HP of 6 and a damage of 15, so that's a score of 21. So now if we go another one, now this one, Website, has a friend in the left who's named Dislike, and Dislike is very powerful. Dislike is a lot more powerful than Website. And Dislike went to the left, because lefty larger is the rule of our binary tree. Now let's see if we can get somebody smaller, righty smaller. Do we have a righty smaller? No, but we do have somebody who's smaller than Dislike, and that's not hard. Shoes. So Shoes we can see Shoes is bigger than Website, because Website has a score of 21, and Shoes has a score of 31, so that's bigger than Website, but it's smaller than Dislike. Now remember, the score is what I'm getting by summing the damage and the HP. And, well, yeah, and then these pocket monsters are being put in the tree based on their score. I'm going to run this a few more times, and we can explore the tree in the debugger if we want to, just to make sure our add method is working properly. I'm just going to, we're going to crank it to size 16. All right, so in our root, we have something on the left, and we've still not got anybody weaker than Website. If I just keep going right, this is how I find the weakest possible, right? The weakest possible one who isn't Website still has a score of 25. So Fence is the weakest one we've seen since Website, but Fence is still not that weak. So I think we were just unlucky this time. We got a really weak starting guy. So let's run this again, and let's get somebody less weak this time. Okay, so in our tree, we've got we've got a root, which has a left and a right. So let's just see Barbecue. Barbecue is 49, so that's pretty good. Barbecue has a score of 49. Now, lefty larger, so lefty better have a score better than 49, right? Cone! Last time we saw Cone, don't mess with Cone. I'm personally afraid for my life just looking at that. I'm going to close that, but let's just remember that Cone is absurdly powerful. Cone definitely deserves to be on the left of Barbecue. It's lefty larger, lefty larger. All right, right? Data. Running. Yeah, running, that's pathetic. Running is obviously way weaker than Barbecue, and there's no way that running would ever beat Barbecue in a fight. That's why running has a weak score of 28, and Barbecue has got a Chad-like 49. So now we can see our binary tree is indeed using its properties for adding properly. Now, we can see that the same sort of logic applies in this visualized binary tree. Excuse the lack of a visualizer for the binary tree. This tutorial. That is me being caught lacking. But yeah, we'll spam add here. We can see that this one also follows that rule. And now that we can see the rules and we've kind of familiarized ourselves with them, can anybody kind of tell me how they think that they might, let's say, find the smallest element in the tree? I'll take that as everybody thinks this is too obvious and knows the answer, but just in case somebody doesn't, I'll go through and I will try to show it off as best as I can. So how do we know it's the smallest? Well, we know, in our tree it's lefty larger. Here it's lefty lesser. So lefty lesser, go left, 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 and look at that. The smallest one is just the furthest one to the left. Now here they have righty is higher, so right, higher, 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 242, so that's the highest. So you can see it's really easy for me to find the largest or the smallest in the set, because all I have to do is go all the way to the right or all the way to the left. And that gets me straight to the biggest one. And also notice that the size of our tree is 50, right? It's 50. But to get the smallest one, I'm doing it in 1, 2, 3, 4, 5, 6, 7, 8 steps. So I don't take 50 steps. It's not O of n. It's a lot faster than O of n. It's technically unbounded, if you will. It's the uppermost bound is O of n for finding the largest here. That's if we happen to have a tree which was added in perfectly sorted order. It's kind of ironic, but if you have things that are already sorted and you add them to a tree, that's going to be like the worst case for the tree. But here in this situation, we didn't add them in a sorted order. We added them in a random order. So it's going to be a lot better than O of n. The best case is O of 1. The worst case is O of n. And here it's a lot better than O of n, but a lot worse than O of 1. And it's pretty close to O of 1 here. It's just O of 3 here. It's pretty good to get the largest, because we just happened randomly not to get very many large ones this time. And yeah, you know, hopefully a simple idea there. And you know what? Why don't we go off track a little bit here, and I'll even write a method to get the largest. And I'm going to make it really simple. Public, or let's call it E largest. And now I'm going to say, I'm not even going to use recursion. I'm just going to say, well, I'm going to say if root equals null, return null. Now I'm just going to say while node tree node e temp is equal to root, while temp dot get largest lefty larger, right? So while dot temp dot get left is indeed not null. Null temp is equal to temp dot get left. That's going to get the leftmost one, and now we're just going to return temp dot data. Temp dot get data. Yeah. Right, and now why don't we just print off, or we'll system out print line tree dot largest every time. So system dot out dot print line tree dot largest dot get damage plus get plus tree dot largest dot get HP. Now here I'm just going to see if our largest algorithm indeed was as simple as I said. And it might null pointer exception. Yep, so our largest is slowly increasing. It's going 30, 96, 96, 122. It's repeating because sometimes the one it's added is no longer the largest. Now if I just want to prove that largest is indeed actually the largest, I'm just going to breakpoint here again. And we're going to compare the output of largest to what's actually the largest guy in our tree. So here we've got a tree of size 1. The tree has a root of, with a score of, ooh, robot, very powerful, 109. And our output here, or not 109, 111, I can't even add. But yeah, our largest is indeed the root, so that's fine. Now we've added a right, which is weaker. And it's going to be hard to beat robot, honestly. The left is just going to stay null. But, oh, we've got a stronger boy. We got a stronger one. Nuclear! Nuclear is, I love these words. So nuclear has a score of 115, it's stronger. Now we go through and we wait and we wait and we wait. Are we going to get anybody stronger than nuclear? 122. All right. Do you have somebody stronger? Is somebody on the left of nuclear? Yes, they are. And their data is plants. Ooh, you don't mess with plants. All right. But the right one is definitely going to be weaker, right? Yeah, whale. Whale has a score of 97 plus 21. 7 plus 21 is 97 plus 21. 118. So whale is pretty weak compared to our good friend nuclear and plants. Okay, now we see, actually it's not weak compared to nuclear. It's strong compared to nuclear, but it's weak compared to plants. All right, so that is our largest method. Very fun. How do we do a smallest method? Well, remember, binary trees are very much a symmetrical kind of deal. So we can easily make a smallest method here. Smallest. And all we have to do is just say get right and get right. And since these methods are so darn similar, I'm not going to test it at my own ire, and I'm going to realize I wrote a null pointer exception, but oh well, too bad for you guys. All right, there's my smallest and there's my largest. I just say this because we got to get to our fun part, which is the in-order traversal. This is the big boy. This is where the fun begins. We're going to start off and we're going to work with stacks. Why stacks? Because I can push to a stack easily. So yes, I do pass lists here, but because I want to be more formal today with us, and I want to show this exactly the way we'd be shown in a class, I'm going to just quickly change these off to stacks. Stack, 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 stackity stack. All right, so now we've got a bunch of stacks in here. Now I'm going to say stack e working stack is equal to new stack. Now, why do we use a stack? We need to be able to add to our data set in O of 1. So every time we do this recursion, we're going to add something to the stack. We need our add to be O of 1, and we don't care about the middle. We only care about adding it to the top of the stack. And a stack helps us reverse things, or not reverse things as well, using enqueue, dequeue, push, pop. I believe the Java stack, well, I think we could use a double-ended queue if we really wanted to be pedantic. Anyways, we just care about O of 1 adding. That's why we're using a stack. Thank you for the question. Now we're going to return in order, but now we're going to pass it our root, and we're going to pass it our stack, our working stack. And that's going to start the recursive step. Now remember, I'm hiding the recursive step because I don't trust anybody with my nodes except for myself. I can touch my nodes. You can't touch my nodes. Only I touch my nodes. You touch your own nodes, please. All right. So how do we do our in-order traversal in here? Well, it's actually a very simple thing. I'm going to show you before I write it. Let's spam remove, get rid of this damn tree, and I'll show you guys a quick in-order traversal, and your mind will be blown as to how easy it is. All right, add random cat. Oh, come on! Why? Let's make a tree that's proper. Okay, here we can go in order, and we're going to go smallest to largest. First things first, how do we get our smallest? Well, we just wrote that. We go all the way left. So let's go left, 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 left. First thing we're going to add is 3. In fact, I'm going to just traverse this with Notepad. No. I'm going to traverse this using one of the greatest IDEs of all time, the only one that is indeed greater than IntelliJ. So, first thing we're going to add is 3. Now, the algorithm we're following is we're going left, center, right. So there is nothing left of 3, so we add nothing, right? So I guess it's going to be null. I'm just going to say added null here because, okay, so less than 3, or left of 3 dash nothing. So center of 3 dash 3. Right of 3 dash 108. So I'm going left, center, right, starting from the leftmost thing. So left, center, right, left of 3 is nothing, center of 3 is 3, right of 3 is 108. Now I'm just going to go up one step, because I was just doing left, center, right on 112, right? So this was just the left subtree of 112. Now I'm going to go 112, I'm going to do that subtree's center. So now it's going to be center of 112 is 112. Now, I've done the center, now I have to do the right. So right of 112 is, well, recursively it's 133. So this is actually technically the center of it, but since it's just like this, I'm just going to shorten this. I'm just going to say right of 133 is 177. Now we would do the lefts if they were there. So now we'd go back up our recursion and we say center of 190 is 190. And we go up another one, center of 192 is 192. And then we go right, left is larger, right? No, right is larger, oops. Right of 192 is going to be 211. And now we got our in-order traversal. Now I understand that might have been confusing to some of you guys, but let me explain it once again in a more algorithmic way. We recursively go through starting at our root, and we say, give me the left. And the left says, okay, give me the left. The left says, okay, give me the left. The left says, ooh, I have no left. I can't give you a left, so I'm just going to give you myself as tribute. And then it's like, okay, what's on your right? Well, the right is going to be bigger than 3, but it's going to be smaller than 112, because necessarily, to become on the left of this, it has to be smaller. But to become on the right of this, it has to be bigger. So it adds itself, and then it adds whatever it was to its right. Right? Because it has nothing to its left, so nothing is smaller. So it's the next thing. And then the thing that's bigger than it, but smaller than the one above it, is added. And it can follow that subtree if that subtree is there in the same way. Then we get up to 112. We've added its left. Now we can add its center. Then we add its right. Its right has no left, so we add its center, and then we add its right. This has no left, no right. We just added it. And then we go through and we do that for 190. This 190, we did the left, so then we add the 190. It has no right. The 192, we just added the 190, then we add the 192, and then we add the 211, and we're done. We've got this traversal in order, comme ça. I will make that bigger for you guys so you can see. And if anybody has any questions, I'll pause now for you to ask before I move on. So here, we've got our traversal in order, and if I move that over, we can see the tree I was talking about. And now, are we ready to move on? I'll give you guys a few seconds. Perfection. Yes, okay, so when I was doing this traversal, I was indeed just going through recursively. The reason I didn't add these as I went was because I wasn't calling my add method, right? I was just recursing through, and then when I pop out of the recursion, that's when all the adds happen. Hopefully that makes it more clear. I'll show you in the coding, and maybe it'll be more understandable, okay? So, we're gonna close that down. Oh, I shouldn't have closed that down in case I wanted to do another demo, whatever. Okay, in order traversal time, it's gonna be simple. If temp dot, I called it root, that's a silly name. I'm gonna have to rename that. So to rename something, you go refactor rename. You can do this in Eclipse or IntelliJ. So refactor rename temp dot get right is not null. Then we follow through the tree, right? We recurse more down because we want to get to the rightmost node. So in order temp dot get right list. All right. Now, if it is this node, then we just say list dot add or push. You can say push temp dot data. And now we've done the right. Now we can just do the left side. So temp dot get left with temp dot get left, and we return list as well. Now this should do a proper in order traversal, and we'll see if it works or not once we run our tester code. But before we do that, let's just get reverse order working too, or at least get it written. So we'll just do the same stuff because reverse order is very similar, but now we return reverse order instead of in order. And here I'll just rename this to be temp so that as well, so I can reuse the same code, except here we just swap our left and our right. So it's going to be get left and get right. And knowing me, I might have made a mistake as to my lefts and my rights. I always get those two mixed up. So if I did make that mistake, I'll just have to swap my reverse order and my in order, because it depends. If it's reverse order and in order, the only difference is which one is left and which one is right. Now, hopefully this should be, oh, this also should say reverse order and not in order. That would be a bad mistake. Okay, and now let's test if our method actually worked. Are we ready? Oh, wait. No, we can, because we don't have our, we're not using our iterator. So let's see if our binary tree run method will indeed say that we have problems. Okay, it's not told me I have problems, but I might. Let's just, let's print out to make sure. Oh, no, it did have problems. Okay, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it's mostly bad. Let's try to figure out what exactly is wrong with our methodology today. So our in order traversal, we're going temp.getRight is not null. Okay, in order temp.getRight and list. Then in that case, we're adding it to our output, and then we're saying temp.getLeft is not null. In order temp.getLeft list return list. That should be okay, but maybe my left and the right are mixed up. So let's just watch it. I'm just going to print off both values so we can compare them. So we're going to say system.out.println tree traversed dot get I plus, you know, a few spaces so I can see the difference, and then list dot get I. Now we'll see exactly what the heck is up with this. And why it's misbehaving on us today. Give it some time to add our bunch here. Oh, this isn't telling us much. So toString is a useful method. toString will tell us the value of an object as a string, and it'll be applied in print line. So like here I can say public string toString, and I'll say return my score. And I'll just do return, let's just say. Now we'll give it a second to run, and we'll see what exactly it's outputting. Is it in sort order? Is it in random order? What's going on? 78, 126, 118, 112, 17, 77. Ooh, okay. So our... Okay, we're doing our tree traversed, and our tree traversed is the first one we're printing on this side, right? It's going, 118, 1112, 717, 169. So neither of them are in very good sort order. Our compare to is returning my score minus their score. This score is that. Interesting. So the scores should be very much just in a direct order. We're doing Pocket Monster compare to. Our Pocket Monster compare to is returning this dot get damage plus this dot get HP. That's a decent comparator. That's an interesting situation. Score of this is 78, 78, 126, 126, 1112, 717. So neither of them are being very nicely in sort order. Both of them are in a kind of whack order. Let's try to figure out why that could be. So I'm putting a breakpoint debugger here just so we can see exactly what's going on. We'll go through here, we'll put the debugger on, we'll wait for it to get to this stage, and we'll just see our list and our tree, and we'll see the differences between them. So our list is a size 150, our tree is also size 150. Our root here is shower with a score of 1831. Oh, that's why. It's not actually adding them. They're doing a string addition rather than an int addition. Classic blunder. So int damage plus int this dot get HP, and we're just gonna bracket those completely in. Now this should give me a better readout of what the scores are so that we don't have nonsense. Alright, running this. I meant to run it with the debugger. And that's our first mistake. It was just addition of int, which was wrong. So now we're gonna wait for it to hit the breakpoint. Okay, now the tree has a root score of 74, right score of 69, 8 score of 80. Nice. And this one is horse, of course. And then this one has a, I'm just going to go right to see if it indeed is getting smaller. Right. Okay. So it should go 11, 12, 65, 69, 74. Well, 11, more or less, right? Because it's also going to have to hit the right ones. But those ones at least should be in order. Let's see. Now list is tree.in order. 11, 12, 14, 16, 27, 28, 29, 29, 29, 30. So where do these not match up? They appear to match up everywhere. Isn't that kind of weird? Because right here it was saying it wasn't matched up. Let's run it again and see. What it was telling me it failed before. Didn't change anything, but now it appears to be not failing. Now that's really strange because that's actually also what happened last time. But yeah, it's failed at 147. Okay. 122, 122, 119, 119. Failed at index 147. Okay, so what is at index 147? Let's just add this to the same if statement, and let's just see exactly what happens when it fails. I only care about the fail situation here because I want to know where my thing is going wrong, because it shouldn't be, but it is. Nineteen, 23, 23, 23. Oh, I think I see the problem. It's when they score the same, it might not be treating them the same. Let's also throw in the names and let's see. Let's see. Alright, now we're going to add a name to our toString, and that's going to show us if indeed our sorting is also... Oh, no, there's two pluses. If our sorting is also just getting the objects that are sorted, like they're the same scores, but they're different physical, not physical, but like different actual Java objects. Oh yeah, I see the issue. So I've got settings and YouTube mixed up, ice and shelf. Yeah, okay, so they're actually sorting, both of them are sorting them properly by their scores, but our compare to method doesn't take a holistic approach to the object. So this is actually a good little takeaway, that our compare to method is only scoring them based on some of their properties. It's not a complete score. And because of that, these two sorting methods actually have a different way by means they sort, by which means they sort. So the linked list is moving around the linked list from its original order, which was the order it was added in. Whereas we are actually unable to ever get back, well, we could get back the order it was added in from the binary tree, but not necessarily. Like, it would be maybe possible sometimes. But the binary tree doesn't preserve the adding order. The binary tree orders things based on their score upon add. So we don't maintain the order that it came in, and that's why some of these don't match up. And now a way we can improve this is we can improve our tester, because our tester shouldn't necessarily be testing their equality, it should just be testing their it should be testing their score. So instead of dot equals, we could say dot compare to is not 0. So we're going to say if they are not same by comparison, then it's going to fail. All right, so what I had to change was that I said before it was comparing items. Well, now it still doesn't like it. It's saying that the compare to is off. What should it be doing? It should be saying if the compare to is not 0, then it failed. That should be a reasonable thing to do, no? Yeah. Oh wait, that's not even it. That was the wrong place to change the method. That's why it didn't fix it. Silly me, changed it in the wrong place. No, we want to change it in binary tree.java. We want to say if the compare to is not 0. Okay, sorry if anybody got confused by that there. So that's the debugging situation solved. So the problem was I was checking the equality of the objects rather than the compare to value of the objects. What I mean by this is that the sorting algorithms here were only considering compare to. They weren't considering the memory address, the physical object on your computer. So the binary tree had a different order of objects that were equal to each other. And because the order of the objects that were equal to each other was different in the binary tree, it gave us some false positives on the failing of the test. Now, since we're actually using the same comparison as our sorter, see here we're sorting it using compare to, and we are sorting using the binary tree, which also uses compare to, it's actually working okay. And now we can just, to be satisfied, look at our identically, or not identically, but by score is okay, so, like, okayly sorted lists. We can now see if indeed it does not fail, it should not fail. We should see that the scores at every index should be the same here, yeah, like system and barbecue, but their orders might be different. See, website and YouTube here got swapped, even though they had the same scores in barbecue and post. There was, see, 4 things here have the same score, and they're in a different order, but they're still sorted because they're in the same, they have the same score. Now, if we want to use a data structure that isn't Pocket Monsters, if we say used strings, we would never run into this problem. It's just because of our compare to with our custom object. And hopefully that gives us some insight onto compare to and the custom object. And here we've got sort order and reverse order. Now, how do we test reverse order? Well, we could say list Pocket Monster tree reversed is equal to tree dot reverse order. And now we can say, let's see, list reverse. Can we reverse it? No, do we have to write our own reversing method? Oh well, I guess we could. Or we could just say that, let's say if, we'll do a quick test for now. I'm not going to write a reversing method really quick. But I can just say if tree traversed dot get 0 is not equal to tree reversed dot get tree reversed dot size -1 system dot reversed is not reversed. And yes, we could also write a quick reversing method if you wanted to test it very thoroughly, but now I'm just going to give it a failure if the tree's reverse is not indeed reversed. So our reverse seems to be reversed. And the reason I trust it is because it's the same algorithm as not reversed. Now that leaves us with just the iterator, unless anybody else has any questions. So what did I change when I was fixed the problem? I didn't actually change anything about our traversal algorithm. Our binary tree was fine from the start. What I had to change was that my failure checker in my tester was checking if things were dot equals, and it was not checking the dot compare to. And by fixing that, I was able to make my test more thorough because I was checking the compare to values rather than the compare to values that are used for sorting rather than the equality. And off the top of that, I also managed to realize that the binary tree and the linked list add in a sort of different way where the order of adding is not maintained with the binary tree. Hopefully that is clear. Okay, so in has next and next iterator, let's go. I'm going to implement a really slow iterator because we're running out of time, but it is ideal that you would do it faster. So let's just do it like this. We'll make a constructor for our iterator. We'll call it, public iterator. Oh, this is a problem because we can't have a constructor in our anonymous class. So instead of the constructor, we could say just here in our method, which can act as our constructor because it's an anonymous class, we can say stack e in order is equal to this dot in order, and now we can just say return in order dot is empty, and return it's not empty, so that if it is empty we fail, and then we say next we'll just return in order dot peak or dot pop. Yeah, dot pop. Now this should let the iterator also give us an in order thing, and just to test that it does, I'll just say for pocket monster pm in the tree system.out.println pm. Right, now this should at the very end just print off all the pocket monsters in our tree in order, and that's a very bad and slow, not the most terrible possible, because the most terrible possible would separately traverse each time. It just does one traversal, so it's not horrible. It's actually, no, I take that back. It's not a terrible one. It's actually a pretty good one. It takes a long time the first time, but it's O of 1 for all future ones. Oh. Yeah, actually, no, that should be... Why does it not like that? It looks like it's never breaking out of our recursion, and that's no good. So how can I do this fix? Well, I should be using a static one. So I could just say private stack e. I'm going to use it as a field, so it actually updates with this class here. In order is equal to this, or equal to in order. See, this is the difference between an anonymous class's fields and the instance variables in the method that declares it. This was not repeatedly reading that field. It was indeed actually only querying it at the same time, and it was popping from a copy of it every time, I believe. So that would have been non-ideal. This time, no, it still doesn't like it. It still doesn't like what it's doing. It doesn't like the fact that I'm not querying it very well. In order is this. If it's not empty, you continue. The next is popping from the in order. Well, maybe it just does. No, it removes the object from the top and returns it. And okay, let's debug it. Let's figure out why our iterator is not being liked and why we may need to debug it. So we're going to wait for it to hit the debugger, and we're going to debug our iterator as well. So this is a binary tree, size 150. We enter our iterator step. So step over. Okay. So return in order is not empty. So in order is size 150. It's getting 50 more. Okay, let's see. Size 149. It's going to be 124 monster. Okay, and why is the pop not removing it? So step over. Step into. Return in order dot pop. So in order is what? Oh, that's why I did the method call. So actually, yeah, the use of the field or the instance variable should have actually been okay. I think my initial intuition about the instance variable was actually correct, and I second-guessed myself unnecessarily. Indeed, it had been because I did the method call every time. That was a silly catch on my part, and now it's actually printing in reverse order, and that's because I used a stack. And remember, when we prop from a stack, orders get reversed. So how do I do this? I just do reverse order, and that's why both traversals exist. Now, we run it, And also, if you didn't want to do it, you could also do remove first, because since I think Java uses a doubly linked list for the stack by default, if not, you can use your own stack with a doubly linked list, like the one I wrote before. Then you can do, instead of pop, you can just do in order dot get first, in order dot remove first. Pop gets the last one, yeah, it removes things, but here, now it's in order. We got toilet, cone, mail, whatever, prints, blah, 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 website, fence, comics, right? So now we've got a relatively good, I came into this saying our iterator was pretty slow. Our iterator is slow, but it's not horrible. And now that's going, and why don't we also just see how fast our various things work? So let's fill up a binary tree, and let's see how long in-order traversals take. I know I'm going a little bit overtime here. I'll be taking questions after. I'm just going to show you guys the runtime efficiency of this stuff. Or I can say it for next tutorial, but I'll give you a sneak peek at least with in-order traversals. So binary tree string b tree is equal to new binary tree for long I equals 0, I is less than input I plus plus b tree dot add. Is there a string generator here and next? List here. This is what we want to do as a string generator. I didn't actually write a method for it because I didn't think I'd be using it. Silly me. This is what we're adding. Okay, and now we're going to say long start time system.nanotime. Then we're going to time our method, so we're going to say btree dot in order. And then we're going to say long end time is equal to system.nanotime. Then return start time minus end time. I capitalized the S, bad notation. Start time minus end time. Return start time minus end time. And bam. Now let's see how our in-order traversal fares against our various methods. Oh, I ran binary tree. I should have run sorting algorithms. Silly me. So here you have to have the library installed, the runtime tester. I'm just going to run sorting algorithms.java. Now, I want to have in-order traverse as my only thing, and maybe I'll compare it to merge sort and not bubble sort or insertion sort, because I think that those might be too slow unless I have too much hope in our in-order traversal. Now we can see that in-order traversals are, well, let's really see which one is faster. And we can see that even if we turn up our steps per iteration, our in-order traversal is faster than merge sort. So let's think about that. We don't want to merge sort every time, right? And if the traversal in order gets our data structure in order, it is, upon the time of reading it, faster than merge sorting it upon the time of reading, is it not? And this gives us as well a traversable a list of the right size. And we're doing it with the same data structure. Now the only difference is that adding something to our binary tree is not O of 1, whereas adding something to our merge sortable data structure may be. So we're basically saving time on the add and wasting time, or we're saving time on the sort and wasting time on the add. But yeah, here we've got the various runtime efficiencies of our in-order traversal and our merge sort. And on that bombshell, I'll await any further questions, and otherwise I will depart.